Hello, everyone. I'm Dave Coit from Rutgers University in New Jersey, the USA. You know, I'm speaking to you via video from the USA, but to tell you the truth, I'd really prefer to be in Beijing right now. Probably some of the audience knows me. Some knows me very well. Some not at all. But those who know me realize Beijing and Tsinghua University are like a second home. I feel that way. Let me give some examples. There I am in 2014. I've given invited seminars several times, 2008, 2014, 2019. The first time, 2008, I was invited to Tsinghua by Kaibo Wang. Thank you, Professor Wang. I also was part of the IQR meetings and presented 2017, 2019 in Shenzhen, 2023 this year remotely. There I am in 2017. Looks like I'm making a very important point. Although Min Shea on the left, I think he's reading a newspaper or something. And next to Min, though, we see Professor Nozer Singh Purwalla. And some of you know Professor Singh Purwalla died this year. So he was really a great man and a leader in our field. And so here's to you, Professor Singh Purwalla. And kind of most importantly, I was a visiting professor in the IE, Industrial Engineering Department at Tsinghua, 2019 to 2022. And there I am at the appointment ceremony with Professor Yanfu Li. Thank you, Professor Li. Wish I was there right now. Now, as said, I'm from Rutgers University. Rutgers University is in New Jersey, which is circled in red. Rutgers is one of the very oldest universities in the United States. And in the Northeast, anyways, in terms of enrollment, it's one of the very largest universities. Let's begin my talk. Now, all of engineering is based on assumptions. Often general physics and principles, physics principles, but then assumptions are made. We need to make assumptions to move on. I started my engineering career by getting a mechanical engineering degree at Cornell University. In mechanical engineering, we learned things like point masses, frictionless pulleys, springs, where the spring force is proportional. These are assumptions that are made. Are they actually true? Well, yes and no. They're certainly, at worst, very close approximations, and we need to make assumptions to build upon and to advance. Now, in reliability, we also make assumptions. Often, maybe a student learning reliability for the first time, or someone in industry, what are some assumptions? One is homogeneous populations and homogeneous time to failure populations. Another is independent failure times. So if you have a complex system with different components, an assumption is often made of independent failure times. Now, are those good assumptions? Homogeneous populations and independent failures? Often yes, but not always. But not always. And my talk today focuses on sometimes they're not. Sometimes the failure times or the degradation processes are not independent. And that's what I'm going to talk about today. Now, the word dependence in an engineering sense means many things to many people. As I said, I started in mechanical engineering. If you talk to mechanical engineering about failure processes being dependent, they think of a physical dependence. This causes this. Degradation of this causes degradation, a cause and effect relationship. Now, and that's fine. Also, there's economic dependence. What is that? An example would be opportunistic maintenance. We're going to repair one item. We have an opportunity to repair another with a cost savings, or the reverse. Economic dependence could be when money or resources used to fix one component can't be used on another. But what I'm referring to is stochastic dependence. What is that? You have two random variables, in this instance, degradation for some fixed time t, or some time t. And these random variables have some dependence relationship, typically as measured by a covariance, or correlation coefficient. Now, my talk today is on clusters of dependent components, and that would be an example of stochastic dependence. Now, do we care? Again, all of engineering is built on assumptions. Maybe they're not exactly right, but that's what assumptions are. Well, consider this. Consider this simple parallel system, two components. Look at the graph. There's some sort of degradation process going on. When the degradation path reaches that horizontal line, it's a failure, and the failure times follows some distribution. Now, this is a hypothetical example. Both of the failure time distributions are normally distributed with a fixed variance, but I'm going to vary the covariance between T1 and T2, failure time 1 and failure time 2. First, covariance essentially of 0, or a correlation of 0. This is a graph of T1 versus T2, failure time of component 1, failure time component 2. But let's increase that variance and increase it again. Now, the dependence relationship is very clear. This, by the way, is simulation, Monte Carlo simulation, based on those distributions. Now, let's increase it even one more time, probably unrealistically, but now the dependence relationship couldn't be more clear. Let's think another example. Probably many of you know about load sharing, and if you've learned about load sharing, often the professor will give this example of an elevator with 3 cables. If one of the cables breaks, right there, look at the animation, let's do it again. One cable breaks, then the remaining ones have to share the load. And it decreases the reliability. And again, which means the remaining cable needs to carry all the load, which is load sharing. The way we're going to model this, again, you can look at the graph. We have a degradation process. But we're going to model the failure times here with a Weibull distribution. And what we're going to do is define some parameter alpha. What alpha will be is the Weibull scale parameter will decrease by alpha of the remaining 2 cables when one fails. Any of the 3 could fail first. When the second one fails, the Weibull scale parameter will decrease by alpha again. Okay. This is 3 graphs, T1 versus T2, T1 versus T3, T2 versus T3. This is with an alpha of 0.1. If there's any pattern there, or any dependence, you can't see it. Let's increase alpha again. A little bit, certainly in the first graph. Again. Now we can see a clear dependence relationship. We'll increase it one more time, probably unrealistically, but now we see very clearly a pattern that the failure times have a dependence relationship. If one is going to fail early, they all will. Now, do we care? Do we care? How is that going to influence our decisions? Yes, we do care. Consider this. If we have a parallel system and we ignore the dependence, our reliability assessment will be optimistic. We'll think the system is more reliable than it is. On the other hand, for a series system, we'll be pessimistic. And of course, a series parallel or some other structure could be either. So it is important to consider the dependence or the covariance. Now let's even go further. Those of you who know me, and some of the audience does, know I work in system reliability optimization. So consider this formulation. I want to maximize system reliability. We have several constraints. We have some decision variables given by a vector x. Those would be which components to choose, levels of redundancy. Now, if we ignore the dependence, we might get that system design on the top, upper right. Lots of redundancy, potentially less reliable components. The size of the rectangle represents how reliable it is. As we consider dependence more and more, we'll get designs like the one on the bottom. Less redundancy, but more reliable components. So, if you're maximizing system reliability and ignoring dependence when in fact it's present, you'll end up with an optimal design like the top when you want the one on the bottom. Let's review. Now, what do I mean? You've already seen a few graphs like this. If you consider the y-axis, capital X, degradation. What is degradation? We're using the term degradation in a generic sense. Any observable and measurable lack of performance, or deterioration of performance. This shows an increasing, it could be, in fact, could be decreasing. And you see the different lines, those are different degradation paths. These are random, they're not all the same. Now eventually they reach that horizontal line labeled a failure threshold. When that occurs, a failure occurs. You perhaps see those three normal distribution looking things. Kind of not, imagine them being rotated so they're facing you, directly at you. And that would be a distribution of degradation at some fixed time t. And the part of that distribution that is beyond that failure threshold lines would be the probability of failure for that time t. Now, who gets credit? Many people. But in my opinion, Professor Bill Meeker receives my respect and credit for popularizing and doing a lot of the original work on degradation modeling. Meeker, he's been a professor at Iowa State since 1975. Now, I saw a notice somewhere he's retiring this year, so it's almost 50 years. I haven't confirmed that, but I think if Professor Meeker does retire, it will kind of be like when Wei Kuo retires. Just means he'll work just as hard, just hopefully doing more things he likes. But Meeker wrote the first papers, or at least the first papers I was aware of. Of course, I wasn't really actively researching this at the time. And I asked him once, what gave you that idea? And he said, I was a young professor working at Bell Labs, and I simply was given the task of assessing the reliability of laser items that never failed, but they degraded. And like many good research papers, at least from my observation, for maybe the first 10, 15 years, his original work on degradation didn't really generate too much excitement, but eventually the engineers learned it, and it received lots of attention. Now, what are some specific examples of degradation? Well, many. As you can see here, you can read the list. Here's one. This is metal corrosion. These bars you see are called rebars. What's a rebar? A rebar is encased in concrete and used to build bridges, the same bridges you drive on or you see every day. The rebars, though, corrode. The concrete needs to crack first, but eventually it will, and contamination will occur. In the Rutgers Civil Engineering Laboratory, we're testing many, many rebars of different materials in a quest to produce more reliable bridges. The picture on the far right, that's Jianhong Li, a PhD student right now from Chengdu, who is doing his PhD on reliability. And you see him there. Each one of those rectangular concrete blocks has a rebar in it. Now, the great thing about working with civil engineers is they don't understand fractional factorial designs. So they're testing every combination, producing a lot of good data. Fatigue is an example. Wear is an example. Now, how are we going to model this degradation. Again, degradation, an observable and measurable deterioration of performance. Many models. And, I don't have time today because I need to get to my new models, but I need to review a little bit. The original Meeker and Liu model I referred to as a random effects model or a general path model. Most of my work involves monotonic degradation processes, so I use a gamma process, but some degradation is not monotonic, so a Wiener process may be more appropriate. There's others as well. An inverse Gaussian process has become popular. Jisheng Yi is a very prolific author. He's written some very good papers. Now, just briefly, this is for those of you who maybe aren't familiar with degradation. This would be the original Meeker and Liu, the general path, a random effects model. We have this function eta. Look at the equation. We have a population of parts. They're all the same, but the individual unit is subscript I, and we have different time measurements, j. But we see this function eta has two vectors of coefficients or covariates, phi and theta I. Phi is common for all of the components. Theta I is specific just for that unit I, and that creates the diversion or the variability in those functions, and the randomness, I should say. Gamma process is very important and simple in a sense, just between 2 points of time t. The incremental degradation follows a gamma distribution with two parameters, a scale parameter and a shape parameter. Look at the equation for the difference between two different degradation measures. We see a function of time. Now, let me get to what I'm here to talk about. That's dependent degradation paths. Before I do that, I want to promote and advertise this brand new paper, Dependent Failure Behavior Modeling for Risk and Reliability, a Systematic and Critical Literature Review. Jiguo Zhang, Ann Barros, myself. Jiguo Zhang, you see the picture on the top. He's a very innovative and successful professor at Centrale Supérieur Université Paris-Saclay in France. His PhD is from Beijing University in Beijing. Underneath him is Ann Barros. Professor Barros is the head of the Risk, Reliability, and Resilience Research Team at Centrale Supérieur. This paper, notice it's dated November 2023, and as I give this talk, it's October 2023, so we're looking into the future, and is a very systematic literature review, but much more than a literature review. We look at patterns in research and trends in research with time. We try to categorize research trends, the most published authors, which journals, many things. Now, in that paper, we've categorized the research on dependence modeling. So the first, you look into the left here, the first big category is statistical dependency modeling and mechanical dependency modeling. Within the category of statistical dependency modeling, first we see lifetime dependence. This would be your failure time distributions exhibit some dependency relationship. Next, you see system state models. This would be your Markov chain, fault tree analysis. Then you see degradation process models. That's what I'm interested in. That's certainly what I'm interested in my talk today. Well, I'm interested in all of them. That's what I'm interested in today. The figure on the right, this is just for the most recent papers. This is a mapping of keywords, and what we've tried to do is subjectively categorize. That's the different colors you see. Now, what are some ways, again, what are some tools when you have multiple components in a system, or there could be multiple failure mechanisms, but for me it's components, and they're not independent. They have degradation paths that are not independent. How can we model those? Well, there's many ways. Certainly many researchers would use a Markov chain. requires some simplification, some definition of state space. Shared shock exposure models, which I will talk about only because I was the author of many of those papers. You can have a joint distribution function of the degradation at some time t. That's difficult to do, but you can. I mean, theoretically. Or you can approximate that with the Coppola function. You can also have a random effects process, or random effects stochastic process, or degradation process. What is that? Well, you could have a stochastic process, a gamma process, a Wiener process, but one of the process parameters is itself a random variable. And how you define that random variable can introduce this dependence relationship. And in fact, one of my new models with my co-authors and colleagues does just that, based on an extended random effects model. Not talking about machine learning. Today, I don't consider myself a machine learning expert, although I now have quite a few publications, but that's generally due to my colleagues and students. And let me call attention to this book. This book came out this year, 2023. This was in honor of Professor Huang, which many of you know, from Chengdu, UESTC, for his 60th birthday. If you're listening, Professor Huang, happy birthday. But in this book, and a credit to Yu Liu and the other co-editors who did an outstanding job, myself, Zhenhong Li, Chenyu Han, we wrote one chapter. And it's a tutorial. It's kind of a tutorial, you see it on the far right, on different methods for dependent degradation modeling. Now, what I'm going to do next, it's not a comprehensive review. I don't intend it to be. I'm going to describe the papers that influenced me and allowed me to build the clustering model, which we'll end my presentation with. First, just very briefly, a Markov chain, because I know many people use this approach, and certainly in reliability, a viable approach for many types of problems. Could you use this? Yeah, sure. In this simple example, we have two components, each have three states. So it's a degradation, new, partially degraded, failed. And the way you define the transition probabilities between states, as the transition probabilities may increase as perhaps the other components in the system have degraded, you could introduce a dependency relationship. Difficult to do, in my opinion. Others may disagree. If you have many components, you have many states, and there's many transition probabilities to define. Degradation is generally continuous, so you would have to define these states. Let's move on. Now, the shared shock exposure models, these were largely papers, originally anyways, by myself and my colleague Xianmei Fong and our students. And so I do want to talk about these. We have a system, and all the components are degrading, and periodically the random shocks hit the whole system. Now, when the shocks hit the system, it affects all of the components, and since the number of shocks is a random variable, that introduces a dependency relationship. Let me explain. See this figure? At the bottom part of the figure, you see a series parallel system. Now here comes a shock. Watch carefully. And another one. Now, do you notice the shock hits the entire system? Every component is affected. And when the shock hits the system, each component can fail due to the shock itself. It may surpass some threshold. But if not, there's some incremental amount of degradation that takes place. And they all receive it, since the number of shocks is a random variable. If there's many shocks, all of the components will, perhaps, in a probabilistic sense, have higher degradation. If the number of shocks is low, less. That introduces the dependence. Very quickly, this would be just for one component out of all of them. But you notice the upper graph is the degradation, continuous degradation together with these incremental shocks. The lower graph is the shocks themselves. But notice, every time there's a shock in the lower graph, look up. And in fact, there'll be that incremental increase. Each component can fail due to a soft failure or a hard failure. That's why we say they're competing. We have dependent, competing failure processes. Now, for each individual component to be reliable, and again, this is just 1 out of n, look to the right, and we see it has to survive all the shocks. But even if it survives all the shocks, each shock introduces that incremental increase. And that introduces the dependence. Very quickly, and I apologize, I've avoided slides like this. Most of you who know me know I'm a professor. I teach classes in optimization and reliability, so there'll always be 1 or 2 slides like this. For a series system, for this system to be reliable, each component has to be reliable. And by the way, this method isn't limited to series, not at all. This is just an example. So for each component to survive, it has to survive all the shocks. Those are the W, the random Ws. In addition to that, it has to survive the continuous degradation with incremental shifts. Then intersect, not multiply. These aren't independent events. Why? Why aren't they independent? That's because of capital NT. Look to the equation. Every one of those components has that NT, which is the number of system-level shocks. How do I solve this? Not too hard. I'm going to condition on the number of shocks, and then sum. And once I condition, these other events, hard failure and soft failure, will become conditionally independent. Now, not independent, but conditionally independent based on the number of shocks. And there's this final reliability equation. I'm biased, it's my paper, but I think the equation in the blue box is one of the most important contributions. We've extended this many times. I just wanted to call attention to this one extended paper from 2019 with Nushin Yousefi, myself, Xianmei Feng, Sanling Song. Now, look at the graph. There's going to be an animation. The failure threshold is fixed. The on condition threshold is a decision variable. So we have formulated this as an optimization problem to minimize the cost rate by changing the on condition threshold for each component. Think about it. If the on condition threshold is too low, you'll never get an unscheduled failure or be very unlikely, but you'll be replacing components or items that still have useful life. Wasteful, perhaps. If the on condition threshold is too high, you will have unscheduled maintenance or failures at the system level, and those will be costly. Now, I've grouped together multivariate joint distribution functions and random effects stochastic processes, even though they're very different, but often they lead to the same place. Again, this is not meant to be comprehensive. In fact, I'm reviewing only those papers that were useful to me to developing the clustering models. First, we have this paper. This is a kind of a simple model. Xu, Chen, Wang, Tong. This is a Wiener process. There's only 2 components, C subscript S, 1 and 2. And as with most Wiener processes, there's a drift term and a diffusion term, but let's look at them more closely. The drift term has this parameter alpha. And notice alpha doesn't have a subscript S, where the others do. And so alpha is shared by both components, and alpha is a random variable. Here it's normally distributed. And so as alpha goes high, both the Wiener processes for both components are affected. That introduces dependence. The first paper I'm going to present to you of our clustering models, it is very different. It's a gamma process that looks extremely different, but it shares a common thought. And so I would say it's influenced by this. Another paper, again, you could argue it's a simple concept, but it's a good one. This is a 2021 paper. Bin Liu, Pandy, Wang, Xiao. Hope some of you guys are in the audience, and if you are, this paper has influenced me. We have 3 independent gamma processes, Y1, Y2, YU, but 2 components. x1, which is the sum of y1 and yu, x2, the sum of y2 and yu. So yu is shared by both of these. So I can condition on yu, integrate, and very easily I can get a joint distribution function for those two stresses for this dependent relationship. Now, my second model I'm going to show is a direct extension from this paper. Continuing on, here's another paper. This is a paper with Liu, Wang, Huang, Yi. Why IJK? This, instead of just a component, it's a system. It's a system with n components. There's j copies of that components, and subscript k is different time increments where data is collected. And it's a general path model, a Meeker and Liu type model, which isn't surprising. Yi Li Hong's PhD advisor, in fact, was Bill Meeker. But here we see these parameters omega. And the omegas have a multivariate normal distribution with a variance-covariance matrix. That introduces the dependence. Very similarly, except for this time we have a Wiener process. And this time, though, we still have this omega term, but now we approximate with a Coppola function. Now, I don't have any other examples of Coppola functions for dependent degradation behavior, but there's many. I recall a paper Wen Jianzhu has written that I've referenced many times. There's many others. Now, finally, my new models, an extended random effects stochastic model and a superposition of gamma processes. They're models with my students and colleagues. The first one, this was published in RESS 2020. This is where we introduce this concept of clusters of components. Let's proceed. Now, here's 4 components in a series system. These are 4 simulation runs for the same system. Now, look at the red and blue. Now, it isn't that the red and blue on average is higher than the other two. It's that they're together. That's what I mean by a cluster. The first 2 graphs, and these are 4 simulation runs, randomly generated, is that they're together. If blue is high, red tends to be high. There's a dependency relationship among them. Components 3 and 4, same thing. There's 2 clusters. So there's a dependency relationship, 2 clusters. How do I model this? Well, it's not quite like that Shu paper with the alpha term, but similar, a similar idea. So random effects gamma process, each component is a gamma process, but we see the scale parameter theta I, theta parentheses I, and it's given by an equation. And look inside this equation, you see these terms theta 1, theta 2, theta k. Notice there's no subscript I. Those are random variables for cluster 1, cluster 2, etc. In front of each of those thetas is an alpha term. That's a sensitivity coefficient. If a certain component does not belong in a particular cluster, alpha is equal to 0. If it's partially in one cluster, alpha corresponds to that partial membership. Now, a component can be in 0 clusters, 1 cluster, or partial members in more than 1 cluster. Now, realistically, how many clusters? Well, for many applications, 0. Don't need my paper. And 1. 1 would be the most common answer. In fact, when I first wrote this paper, we limited it to 2. And I kind of wish I left it that way. The models would have been more understandable. But before submitting, we generalized it to k. That's the way I think. Here's some example of a reliability graph. I think this is a good model. It's complicated, perhaps overly complicated. You would need a lot of data to estimate these parameters. If you have enough data, we can, in fact, and have developed a likelihood function that we can maximize. But in truth, this is a complicated model. I wanted an easier model. So we've worked on this. Now notice this Li, Coit, and Zheng, 2024. So it doesn't exist yet. Well, it exists, just not in a final form. So that would be Zhenhong Li, myself, Jiguo Zheng from France. The way this model works is this. There's two submodels. First Model 1, then Model 2. Model 1 is a direct extension from that Bin Liu et al. Paper. In fact, Model 1 would be, it's not worthy of a journal paper. It'd be a conference paper. But you'll see we do more than that. In this instance, instead of two components and one cluster, cluster's my term, we have n components and m clusters. However, each component can be in exactly 0 or 1 cluster, full membership. Now, we can very readily, given those assumptions, condition again on the clustering, random variables, integrating, we can very quickly get a reliability function. And from the reliability function, we can get a cost rate function. And you see on the graph on the right, that's what we see. And we can minimize that cost function. But let's extend it to Model 2. Now, Model 2 is a generalization of this Model 1. Now, look at the equation. Every component can be in multiple clusters. The clustering gamma function are the W's, with a parameter governed by this matrix capital A. If that small a is a 0, it's not a member of the cluster, and often that will be the case. Now, this model is straightforward. It's easier to understand. It's easier to quantify. I still need a lot of data. Here's a general reliability function for a series system. We can do something similar for any system structure. So this is my current research. Now let's see how it works. Now, look at this graph. These are 4 different alphas. As we go left to right, the dependence increases. Now there'll be 4 simulation runs. First, look at the left. Is there any pattern? Just look at the left. Ignore the other ones for now. No, not really, between the 4 components. Now look at the third one. I'm going to keep doing the simulations. Oh, we do see. And what again? We like here, red's by itself, but we start to see 2 components, the red and the blue, are often together, and the other 2 are together as well. Now, let's go all the way to the 4th one. That's an extreme. That's not realistic, but we're trying to make a point. There's complete dependence. We have 2 clusters with complete dependence. In reality, the second or third graph would probably be more appropriate when there's dependence relationship. But you can see we're able to successfully capture the dependence with this model. We're able to successfully model clusters. There can be 2, there can be 3, there can be any number of clusters. And this model then does it. And with some reliability. How many clusters should there be? Well, what we recommend in these papers, if possible, this should be predetermined. So that concludes my talk. Thank you very much. Anything I talked about today could also be done with some sophisticated machine learning models, and I know researchers are working on it now. I know some very good papers by researchers in Netherlands, Mihaela Matici, and others. And that concludes my talk. Thank you very much.